Hello, it's Keith here, and this is the 5th episode of the ChibiAkumas series of my Z80 programming tutorials. Now, we looked last time at the star array and how the bullets were drawn on the screen. This week we're going to move on to the object array. Now, the object array is basically the sprites that are drawn onto the screen, but they aren't just a set of sprites. They also handle collision detection and movement and the firing of bullets and things like that. So the object array is the vast majority of the other code apart from the star array with regard to creating the enemies on the screen. So how does the object array work? Well, if we look back at our memory example before, you can see that the memory is used in a bank here. Now, the object array has up to 64 entries, and each entry needs 8 data elements to define it. And you can see how they're laid out here. And again, just like with regards to the star array, we are storing them in a aligned structure using this set of memory here and this set of memory here. And the theory again is that we can increase H to move down these attributes. Then we can set the 6th bit to 1 to move to these attributes and move back up the array here. And effectively we are starting in pretty much the same place as we started. So this allows us a quick, easy way of reading the data for each element one by one, like we did with the star array. So let's just briefly discuss the data elements that are stored for each object. Firstly, they have a Y position. A 0 means that the object is dead and isn't drawn. And then there's the X position in game units, as we discussed before. Then there's a sprite number. Sprites can be from 0 to 63. The top 2 bits have other meanings. ChibiAkumas supports up to 4 banks of sprites, and so the top 2 bits are used to define whether it's a single bank sprite or a 4-bank sprite or a 2-bank sprite. And on the CPC 464, only 1 bank is used. On 128K systems, all 4 banks are used. The banking was basically to allow the game to work on different systems with different amounts of memory. Animators are an advanced feature added with ChibiAkumas episode 2. They handle complex movements and animation. We're going to look at those separately because they're really a separate element. Then we have a size. In the original ChibiAkumas, all sprites were 24 by 24, but this was very limiting. So I added a size function which allows the hitbox of the sprites to be changed so that sprites can be very large or very small. The size does have to be square, however. Next we have a program. This is usually the fire pattern, so there will be a speed and a pattern, and that will define how often the object fires. However, it does have other special purposes. It's used to define objects that are power-ups, and background objects use a program that defines them as having a half byte movement. That's where, if you remember, I said before that there were 80 bytes across the CPC screen, but we use 160 visible coordinates. Well, we can have the second bank sprite a half shift of the byte and then alternate between them depending on the X pixel. So it's used for making the moon shift half a byte along at a time, which gives it a much smoother movement for those slow moving background objects. And then finally we have the life. Now the life of an object is from 0 to 63, but again the top 2 bits have special meanings. Now an object can either be hurt by bullets or not, and it can hurt the player or not. Now if it's not hurt by bullets, it will be a timed object, and these decrease in life automatically over time. If an object hurts the player, then if they collide with it, the player will be injured, with the exception of the power-up objects. These have to be defined as hurting the player because otherwise the collision detection won't execute, but they never actually decrease the life of the player because when the collision detection occurs, it realizes they're a power-up and increases the player's powers rather than decreasing their lives. So that's the very basic summary of the data that we store within the object array. So how are we going to actually process the object array? Well, just like the star array, it's a loop that proceeds for every object in the array. So the first thing we're going to do is we're going to work out the hitbox. So this is based on the size of the object and the current coordinates of the player. Now, as I said before, the objects can be different sizes, but the way it works is it will use the last size of the last object and it will reconfigure the hitbox if the object size changes. So if all your objects are 24 in size, it will never change. But if the first half of the objects are 24, then the next one's 32, it will reconfigure for 32. And then if the one after is 24 again, it will reconfigure for 24. So it doesn't reconfigure for every object, it reconfigures for every time the object size changes. And that's a bit of a saving there. So once we've worked out the hitbox, we need to seek for the next living object, which we do by just scanning the Y coordinates until we find a non-zero one. Then we read in all the attributes of the object into our registers. Now we execute the animator, which is the complex animation code that is added to ChibiAkumas episode 2. Next we see if the object is in the player's hitbox, and if it is, then we process the player hit routine. After that, we check the object's life, we see if it needs to age naturally, and if not, we will see if the bullets have hit it. Next we scan the player's star array and see if any of the player's bullets have hit the object. If it has, we decrease the life of the object and then kill the object if the life has reached 0. Next we process the moves. Now we looked at the moves before in the do moves command, and so this will relocate the object in a simple linear way. Of course, object animators can do more advanced things. Now we've done all of the changes that are required to the object, so we save all of the object data back into the array here. Once we've saved it, we then run the program, which is effectively going to make the object shoot. Finally, we run the sprite drawing routine. We do this last because the sprite drawing routine alters all of the registers in system memory, so it's best to keep it out the way of the other functions. And then finally, we repeat the entire procedure for the next object. So let's jump to the source code and have a little look at how it all works. So here's the source code of ChibiAkumas. And so here at the very start, you can see the Reconfigure for size command. And so what we're doing here is we're going to be passed the size of the object in pixels, and we're using self-modifying code to reprogram various places, mainly with regards to the hitboxes of the object, with the full size of the object, half the size of the object, and a few other things here. Once we've done that, we then need to reconfigure the hitbox of the player to check if the object has collided with the player. And so what we're doing here is we're reading in directly from the memory of the player's variables for player 1 and then player 2, the x and y coordinates, and subtracting the height of the object and half of the width of the object, because the object is square but the pixels are half the number of units across as down. Now you will notice here there's a 0A command. This is in case there is an overflow. If we've overflowed any of the registers, we need to zero them out, otherwise we would get strange effects there. So that's just to stop anything going over to 255 there. Now here's the main redraw command here. And so we need to check if the game is paused, and the way we do that is we read the timer. The game timer works out what ticks have occurred. Now ticks occurred is a binary value. The bit 0 should occur every tick, bit 1 should occur every 2 ticks, bit 2 should occur every 4 ticks. So if the ticks occurred is 0, then that means the game is actually paused. So we don't update the object array when the game's paused. Now, we've tagged in the particle array for the V9K, which is the fireworks effect. We've put it at the start of the object array just because there's no other registers in use here, so it seemed a good place to put it. Next, we need to reconfigure the object array for the starting size and calculate the new player's location here. Then we set at B to the size of the object array, which will be 64, and we set the pointer to the memory that's used by the object array. We XOR A to set it to 0, because we're doing compares here, which will compare to A, and we're just quickly doing a compare to 0 here effectively. And then we loop around here until we find one that is not 0. When we do find one that's not 0, then we need to limit the position on the spectrum, because we'll get nasty color clash if the sprite isn't on an 8x8 aligned pixel grid. So we're just realigning the Y coordinate here to make sure it is. Then we're storing the Y position for the sprite drawing later, backing up some registers here. And now what we're doing is we're reading in all of the values here, and you'll see here we're inking H, but then when we get to this position we're setting bit 6, and then we start decreasing H. And if you look here, that's because we're reading down here and then back up here, and we effectively end up in the exact same position as we started. So you can see we're loading each value into a different register, because fortunately the Z80 does have a lot of registers, so we can actually get it all into memory in one go. Next we have some quite complex code here. You can see here we've got just setting the sprite number using 0 to 63 bits here, but then we're reading the top 2 bits and we're working out what bank we're going to use. Now this is quite complex, and there is actually more of it later, but effectively what we're doing is on a 2-bank sprite, we're alternating between banks 0 and 2, and on a 4-bank sprite we're doing 0, 1, 2 and 3. So we're getting more animation on the 4-bank system. There's no 3-bank system, it has to be 1, 2 or 4. Next, we're checking the life of the object because that defines if the player can be hurt by it. If it's not, we skip over the next bit. But this is the collision detection routine for player 1. We just check if the object's X and Y coordinates are within player 1's hitbox. Then we check if player 1 is alive. If player 1 is alive, we load in the player's variables here and call the hit routine. For player 2, we do the same, only we load in player 2's variables and call the hit routine. That means the hit routine can be common for both players because this player array in HL would define which player is being hurt or powered up. You will notice that we check if the player's alive last on player 1 and first on player 2. This is a bit of an optimization. I'm assuming player 2 won't be playing and player 1 will be playing. So this kind of makes things more as efficient as possible for the 2-player code. You've got to bear in mind, the original ChibiAkumas was 1 player only, and it was already fairly slow. With ChibiAkumas 2, I had to add an extra player, and also a lot more complexity in general, but try and make the game at least as fast as it was, and I think it actually ended up quite a bit faster. So it took a lot of optimization and tricks to try and get things faster than the original, but with the extra player as well. So after we've done the player hit routine, we do check if the object itself is still alive, because if a coin has been hit, the coin will be killed and that will set C to 0, and we just need to check if the object is still processing, because we don't want to carry on processing if the object has been killed, because we might actually bring it back into play by accident. So this is the routine that checks the life of the object. So the top bit defines if it's hurt by bullets, and we'll be checking that here. And the next bit defines if it hurts the player, and we checked that up here. The remaining bits are the life of the object itself. If we are in this route, if we get to this point, we need to check if the object needs aging or not. Now, I should say an object with a life of 0 is an immortal object. It will never die and it doesn't hurt the player. So this is background objects and things like that. But it's also used occasionally for enemies, for boss enemies, because a boss enemy isn't just a single object. Things like Zombie 2 was actually 3 objects, and some of the very large bosses could be a dozen or more objects. They're all just moved in tandem, so you can't see the gaps. And then a hitbox object, which is an invisible object, will be used to detect the bullets that hit the enemy, and then a separate life counter outside of this will be used to count the life of that boss enemy. So in some ways, in the boss battles, the object array is basically used like the hardware sprites of a system like the Game Boy or the NES, but of course they are software sprites, but they're used as a controlled set of sprites that are moved in patterns, and then the hit calculation and things is done separately because the boss battles are much more complex than the run-of-the-mill enemies. Here we're just checking if the object has died after the life was decreased. If it has, of course, we just skip over the rest of the code. At this point, we are now checking the player's bullets. So what we need to do is do our hitbox detection for the object itself, depending on the object size, again using self-modifying code here for speed. Then we back up all the variables that we're going to need later, and then we scan through the entire bullet array of the player, and we just see if any of the bullets have hit the object. Now, it is important to note that, as I said before, a bullet within the player's star array, the top bit has a special purpose, and that's to define which player actually hit the object. So at this point we're just checking to see what bullet hit the object, and we're defining this shooter variable here, so we give the coin to the person who actually successfully killed the object. When a bullet hits, it's removed here. It should be noted, however, that we only scan for the first bullet that hits an object, and that's why you may see bullets fly through sometimes. The reason for this was simply time saving. If an object has been hit by the bullet, rather than scan the rest of the array as well, we might as well just move on and carry on with the next one. We could have removed all the bullets, or even downed the object's life by as many bullets as hit it, but I decided that I wanted the enemies to be quite hard to kill, so I wanted it to take some time, and I thought, again, saving time scanning the rest of the bullet array, if we'd already found the first bullet that hit, made more sense to me, so that's what I did. At this point, we then restore our variables because we need to carry on with the rest of the loop, so we need to undo the register changes that occurred here. Now you'll see there's a bit of tricky self-modifying code here. We've got a jump relative that will skip over this code here, but if the object was hit, we will have reset that just here, and that makes this run this code in the middle, which handles the decreasing of the life of the object. So rather than loading a register from memory or using self-modifying code to load a register, I'm actually self-modifying this jump here, and I'm using a JR because that's shorter than a JP. But it should be noted, self-modifying code on JRs is a bit tricky because if you do it wrong, you'll jump into some random nonsense and you'll get a crash. So you do need to be a little bit careful there. Now we're going to do the do moves command. This is the command that we looked at before. We need to load D with our do moves register because that's what do moves expects, not this IXH. When we get to this point, we've actually completed all of the processing of the object and we now need to save everything back again. So we skip over these two because they never change. And then we save the new program code and the life and the sprite. We have to switch back to the first part of our array here. And then our move and our X and our Y. The move and the program code can be changed by the animator, you see. Now at this point, we've saved all of our new variables and finally we run the object program, which will do the bullets of shooting. Again, we do this last because we don't need to worry about our registers then. The program can't change the position of the object, which is why we can do it after we've saved all of the other attributes here. Now once we've got to this point, we're ready to start working out how we're actually going to show the sprite. So we've got a lot of code here which works out the bank and also works out the memory location and the physical bank within the system, because of the 128K systems need bank switching. So we've got a lot of code here with regards to which memory bank within the system it is and the memory address of that bank, because at the end of the day, in order to show our sprite, we know we need to set the starting address of the sprite binary data in this bank address attribute. We need to switch that bank into memory if it's in a 128K system, and then we need to run the show sprite command, and we also need to reset it back so our system doesn't crash. On the ZX Spectrum, it's basically the same, although we have to be a bit more tricky because the memory is much more limited on the ZX Spectrum. But finally, on the MSX, we do have an extra attribute. The Y position is an extra thing on the MSX because the sprites have a data block that defines the position of the sprite and the size, just like on the CPC. On the MSX, the sprites are actually held in video memory at a Y position, and this is the Y position of that video memory. At this point, we're now back where we started, and all we need to do is reset A to make sure that that compare works again, because we do compare C, which relies on A being 0, and we jump back to the start to continue with the loop. And there we go. Now, if you want to see an example of the object array creating a sprite, I'd suggest you have a look at the previous lesson where we looked at the movement and we created a very simple object here. At this point, I don't think it's worth doing any more tests because we're going to be having a look at the event stream, which is the level code that creates objects later. And it's only really at the point where we understand the event stream we can really start to look at objects in more detail, because objects aren't really ever created without the event stream doing the work for us. So there we go. Well, I know this is quite a complex lesson and I apologize for that, but this is the nature of the beast, so to speak, when it comes to coding the game code that handles the sprites and the bullets and the movement. Now, if you think about it, it's quite complex what we saw, but the amount of work this is actually doing is quite immense. Once you've got the bullets code and the object code here, you've actually got the entire enemies of the game. It's just the level code, the event stream as it's called, and the player that add the final elements of the playable game. Anyway, we'll be looking at all of that in later lessons. I hope you've enjoyed this week's lesson. If you have, please like and subscribe to my channel. Anyway, I hope you'll join me next week. Thanks for watching and goodbye.